Hello. Here I will explain the full Gauss algorithm. For solving systems of linear equations without any restrictions. A generic system will, say, have n unknowns, x1 up to xn. And the typical linear equation on those unknowns will have these coefficients a11, a1n throughout, and then on the right hand side b1. And then we could have many such equations. Say we have m of those. So that is the shape of a system with n unknowns and m equations. As I was saying before, the convenient way of solving it is to replace it by its extended matrix. Just recording the coefficients. In the bulk, there will be the coefficients of linear expressions of unknowns from left-hand sides, and in the extended part, there will be three coefficients on the right. So that is what is called extended matrix of our equation. And then what we're going to do, following this Gauss algorithm, we're going to transform it using elementary transformations to its best possible shape. And the best possible shape will allow us to see solutions. And transformations will be such that they will not change solutions of the system. So these elementary transformations or Gauss transformations are our tools. And there are three types of that. They can be grouped into three classes. The first is just transforming one of the rows of our matrix. Say the first one. And that is a transformation which just takes a row and multiplies or divides it by a number. So I will write multiplication by c. But multiplication is the same as division if we use the inverse as a factor. Only the first one changes, the rest of the matrix stays as it is. So that will be scaling of the first row. Row scaling is the first type. The second type will involve two rows, so I will just write the first and the second. Again, that can be done with any pair, not necessarily sitting next to each other, but it's easier to write what happens when they are next to each other. And whatever is left in the matrix will not be changed. This transformation just changes the order in which the two rows appears. The first and the second in this example. And that is even easier to see that this transformation doesn't change solutions. And it's still a useful transformation to this row swap. Is a useful tool. For example, if we want to have something non-zero sitting in the top left corner, and original first equation has 0, we can change it with, swap it with any other equation where the first coefficient is not 0. The last type is the working horse of the Gauss algorithm. The last type is most frequently used. It's the transformation which, again, transforms only two rows, actually one row, but we need to know some other row to do this transformation. So still I'm recording two first rows in my matrix. The transformation can be applied to any pair of rows, not necessarily sitting next to each other. The transformation is of row addition type. So I will be transforming, say, row 2 with the help of row 1. And the transformation is just transforming only row 2. It will take whatever other row I'm using, I will have to scale it with this coefficient and then add component-wise to the row I'm transforming. And the rest of the matrix will not change, but the only changes will occur in the transformed row, the second one in my example. And the transformation graphically is easy to perform. We just see the row we're transforming it with, we're scaling it by coefficient, but not keeping it in the matrix, but just taking it out, sort of, and using it to change the second, scaling it with coefficient and adding. And throughout I will see this effect. The free term has to be transformed as well in the same manner. The rest of the matrix doesn't change, including the first row which we used to transform the second. So that is a transformation which is a matrix record of substitution, of taking a variable in the, say, first equation and substituting in the second for a special choice of C. But in general, it is a transformation which just takes the first equation, multiplies it by this number and adds to the second equation, keeping the first equation intact. Such row addition doesn't change the solution of the systems. So all three types of transformations don't change solutions of the systems simply because we can undo them. So whatever changes we could have potentially will have to be none because we could undo them, and again the changes will have to be undone. So that simple fact that these transformations are reversible, and for that reversibility, the coefficient which we allow to multiply by has to be non-zero here. The swap is always reversible, just swap back. These transformations are again always reversible. If we add to row 2 row 1 with a coefficient C, we can undo it by subtracting row 1 from row 2 with the same coefficient C. So we just replace C by negative C, and we will get a reverse row addition operation. So now with this at our disposal, we could see how generic matrix can be transformed to a better shape. Again, I'll start with the generic matrix. Now I will not be calling my entries some names. I'll be just using stars to represent something interesting, something non-zero happening. So the first step is to transform the first column and make it to contain as many zeros as possible. And the first step in doing this transformation of the first column is to create one. We can create one by, say, row scaling if we have something non-zero in the first column. If we don't, we just have the full zero column and we proceed to the next one. But assuming that we have something non-zero, we can create it somewhere in the column. We can find it rather somewhere in the column. We can scale it down to 1 using the first type, and then using the second type, we can move this one to the corner position. So still I have something interesting happening elsewhere in the matrix, everywhere else. Then continuing with transforming the first column, now I will use the last type, row addition or subtraction transformations. With the help of the first row, I can get rid of all the components of the first column in all other rows. Whatever happens to sit in here, I can make 0 by multiplying the first row by that very number and subtracting the first row from the second. And all others are done analogously. So that is the first step of the Gauss's algorithm to transform the first row into this shape. And then we are left with the matrix, which is one size smaller in each of its dimensions, and we continue in the same way. So we look at its first column and again create, if it's all zeros, we proceed to the next column, and if it is not, we create one and eliminate. So this Gauss's algorithm is also called Gauss's elimination algorithm because we eliminate as many column entries as possible. And continuing doing so, we will create what is called a row echelon form. So we'll have one, say, sitting in this position. We might have 0 columns, like 0 column here or 0 column here. So we might have the line of zeros beneath, and then sooner or later we might have one again, and so on. So this echelon shape for rows is what makes this matrix row echelon form matrix. So below the line, below the staircase line, are all zeros. And now we already see something about our variables. So those columns in the extended matrix, in the bulk part, they correspond to unknowns, to our variables. So the first column is the column of coefficients of x1, and all the way down to the last, which is a column of coefficients of xn. So now we're seeing some special columns in this row echelon form, and these columns where the corners of our staircase shape are located are called pivots, or pivotal variables. So whatever is not a pivotal variable, whatever is not a pivot, will be free. And the meaning is that there will be it will be possible to assign any value to these free variables and still find a solution with these values for free variables. So non-pivots are free variables, and they are parameters of the generic form of a solution. But to be able to solve, we have to not have inconsistent, unsolvable equations, like an equation where we'll have all zeros in the left-hand side of the equation and non-zero on the right. In the reduced in the row echelon form, it means that so solvability means that this staircase will have to meet with zeros on the right-hand side. Solvability is absence of the equations 0 equals some non-zero number on the right. So that is, again, easy to see in the row echelon form. After transforming to the staircase shape, our bulk of extended matrix, we could see what happens in the extending part, and if we have something non-zero matching zeros on the left, that is unsolvable. That is the easiest case of solving the system. We just say no solutions. But assuming that we have solutions, assume that this non-solvable case doesn't happen, so non-solvability rather is presence of these equations. If that doesn't happen, then we can proceed to what is called reduced row echelon form. It is basically the same thing as before, but we will make it even nicer. So the same staircase shape which we had before, with pivots sitting at the corners, zeros below, but then using row additions or subtractions, we can, starting from the very last pivot, first create zeros above it, and then proceed to the one pivot before that, and then continue if we must. So that reduction, that elimination of coefficients which are non-zero sitting above any pivot will create reduced row echelon form for us. And why do we need to do that is because now the equations behind this matrix, the system of equations, will have the best possible shape. So let's imagine what the equations are. We'll have as many equations as pivotal variables. So we'll have equations having a pivotal variable and just one pivotal variable inside them. Because of these zeros we created in the reducing part of the algorithm, each equation will just have one and only one pivot. And then the rest, whatever non-zero coefficients we might still have in these equations, they will correspond to non-pivotal variables, to these free variables. So they can be made whatever we like. And each of these equations now can be used to compute the corresponding pivot in terms of free variables. So free variables will be parameters of the system, or rather of a generic solution. And then pivots are functions. Linear functions of free variables of these parameters. So that is as best as we could do in a generic case where, say, solution is not unique and we have free variables. The criterion for uniqueness of solution will be just as many free variables as we have, no free variables at all, as many pivots as the variables. That would correspond to the shape of a matrix. So unique solution will correspond to the shape of a matrix like that. The right-hand side is whatever, it's just actually the solution coefficients, and the left-hand side, the bulk, will have to be transformable into the staircase shape where all these stairs have just smallest possible size. We'll have all the steps will have the smallest possible size, so we'll have a diagonal matrix, and after zeros will be below at the row echelon form step, but after reduction we will just have zeros above, and that will be the only way to have a unique solution. Otherwise, as soon as we have free variables, we have infinitely many solutions. So that is it for this lecture. Bye.